Hello everybody, my name is Atan Karabey and I'm a fourth year electrical engineering student in Bilkent. And this is my physics 212 project video. For our project, we decided on muon detector because the relativity for us and for my group was the most interesting subject of physics 212. So let's get to it.
Well, what does relativity have to do with muons? In the grand universe and space, astrophysical sources such as supernovas produce high energy charged particles which continuously bombard the Earth. And when these particles, like proton, bombard the Earth and collide with the atmosphere, they produce lesser particles such as muons. But in classical physics, muons should not be able to reach the sea level. In theory, the path through the atmosphere to the sea level should take more time than the muons' lifetimes. And this is where special relativity comes to rescue. As because muons travel at relativistic speeds close to the speed of light, they experience a dilated time which allowed them to reach the sea level before their lifetimes end. So detection of muon at sea level is a proof of relativity, and this is our main objective. For muon detection, we use Geiger-Müller tubes, two of them stacked on top of each other. Why two but not one? Because Geiger tubes actually recognizes lower energy radiations too. So we want to distinguish the uh, lower radiations from the muon detection. So a detection is counted as a muon detection only when the two tubes are activated at once. And alongside relativity, we want also to demonstrate the zenith angle distribution on this setup. As you can see the formula, the flux of muons is heavily dependent on the path length they must travel through the atmosphere. At the zenith, the path is the shortest. The zenith is when the angle is 0 directly overhead. So by conducting the muon detection experiment at different angles, at 7 different angles to be exact, at angle 0, 15, 30, 45, 60, 75, and 90, we want to demonstrate that this formula actually works. Firstly, a MATLAB code is written to find the optimal coincidence timing window.
The coincidence timing window is the amount of time that we give to the tubes to synchronize a detection. Basically, when a tube is detected as something, we give a coincidence window amount of time to the other tube to detect something too. If two tubes detect something together in this timing window, we count it as a muon detection. This timing window should successfully count all the muons while minimizing the accidental coincidence rate.
Through MATLAB, the optimal coincidence window timing was found to be 100 microseconds. We first tested the Geiger tubes on their own, separately. Later, we put them on top of each other and made the first experiments for the progress report. We did a 22-minute physical observation and 19 coincidence events, the muon events, were recorded, and Tube 1 and Tube 2 registered 327 and 322 hits respectively. To verify that these 9 recorded coincidences are real things and real muons and not false coincidences, we calculated the expected accidental false positive probability. First, the individual count rate is counted like this, which is 0.24, and using the 100 microseconds that we found from the MATLAB, we calculated the total expected weight, which was amounted to 0.015, and this shows only a 1.5% probability of an accidental coincidence occurring during our runtime, which shows that the 19 recorded events are true cosmic muons with high probability. For the final phase of our projects, we designed a custom 3D CAD mounts that were printed to securely lock the Geiger kits at the exact distance we want. As you can see, this is the 3D CAD figure. And after this, at each designated zenith angle, from like 0 degree to 90 degree, data were collected continuously for approximately 2 hours. So for 7 angles, 14 hours of data collection in total were made. Later, we used a curve fitting model for proving the zenith angle distribution formula that we have talked about. We used and compared 3 curve fitting models for this final phase. Model 1 is the textbook cosmic ray law with no additional math behind it. The second model adds an angle independent offset to the textbook model. So along I0, it also has n as the free parameter, which makes it has a 1 extra degree of freedom compared to 1 and 3. And third model takes into account the finite angular resolution of the telescope at our designated tube separation, which was 8 centimeters. Both from the plots and the least square errors table, it can be seen that the Model 2 was the most successful one at approximating the curved line that fits the data that are collected together. These are the final numbers for the model parameters. And the fact that a curved line with the formula of the zenith angle distribution fits this perfectly to the data that we collect verifies the cos-square law, which was the second objective of our project alongside the muon detection.
Overall, we achieved all the objectives that we set before, and this experiment made a great proof of the relativistic time dilation. Thank you for watching.